Hello physics students. Today in this video we're going to talk about the spring force, because the spring force is another one of those predictable forces like the force of gravity or the force from planet Earth, or the normal force or the force of friction, meaning that if a given set of conditions is repeated, the force is the same as it was before and the force follows a pattern. So that means we can describe it with an equation. So that's what we're going to do today. We're going to learn about the spring force and the equation that allows us to calculate the strength or the magnitude of the force produced by a spring. So the first thing I want to point out is that there are springs of different strength, and also the idea that the more a string is stretched, the harder it pulls. So if if we were in class, I would hand you a bunch of springs so you could look at them. So here's one spring, and you see that it's relatively easy to stretch, but if I pull it just a little distance, it pulls with a relatively small force. If I stretch it a further distance and I let it go, it snaps back with more newtons. So the more you stretch it, the more the force is. Stretch it a little bit, you get a small amount of newtons. Stretch it more distance and you get more newtons. So that's the first point. And then the second point is that if I take another spring that has thicker coils than this one, okay, so you see how these are thicker metal, more rigid. This one it still has that pattern. If I stretch it a little distance, I get a smaller amount of force than when I stretch it more distance. But keeping the distance equal, this, if I stretch it, say, 2 centimeters, it's very easy to do. Try and stretch this one 2 centimeters, and it's harder because of the thicker coils. So different springs have different strengths. And then strings can get quite large. This is a spring that is used in a garage door to hold up a garage door so it doesn't fall. And this one, boy, I try really hard and I can barely stretch it because of the thick coils. So those are the points. More stretch, more force for a given spring, and some springs are tougher, require more force than others, okay? The other point I want to make before I move on is that there are some springs that aren't used for stretching, they're used for crushing or compressing. The physics behind and the equations behind those kinds of springs, exactly the same as what we're going to learn for the springs that I have for you today. So before you write this down, I want you to write the title for today, and actually write this first. Okay, so spring force, F subscript S for spring. We had G for gravity, right? N for normal force. And the equation we're going to learn is called Hooke's law. Not really important that you know that, but specifically for all springs, they have a certain relaxed length. We define the location of the end of the spring in the relaxed state as x equals 0. Then, when you stretch the spring, we define this x as how much longer the spring got in the process of stretching it, or how much shorter when you compress it. That's called spring displacement. How much you displace it from that equilibrium, that's x. And if you wanted a mathematical expression, it's the total length of the spring. Like if I went like this and I measured this as 50 centimeters and then it was 20 centimeters, then we would have 50 minus 20, or 30 centimeters would be the displacement. So jot this diagram first in your notes, defining spring displacement under the title. So I'll pause the video to allow you to do that. Okay, so the next thing we're going to do is see the pattern, the equation behind the spring force. So imagine I do an experiment where I'm going to stretch a spring out, a certain displacement, and then see how much force I get out of the spring. So the first thing is with no stretching of the spring, if it's just sitting there, its displacement is 0. I haven't stretched it yet. Then it will produce 0 newtons of force. That's common sense. Okay? And now what I'm going to do is I'm going to take a spring scale and pull this to 5 centimeters in length of displacement. So see, I moved down to the meter stick here is the end of the spring moved to 5 centimeters beyond where it was relaxed. And I see I get roughly about 1.5 newtons for that 5 centimeter displacement. But with this force, we stay in meters for displacement, and we got 1.5 newtons. So again, distances must be in meters. That might require a conversion in a lot of problems. So now I'm going to stretch it to 10 centimeters beyond its relaxed, and I get roughly about maybe 3.2 newtons for 10 centimeters, or 0.1 meters was about 3.2 newtons. So it's not perfect, but notice when I double the displacement, I approximately double the spring force. The reason why it didn't come exactly is because I am dealing with a spring scale that's very crude. And actually this spring scale, the gears I can feel are a little rusted or something or damaged. So now I'm going to go to 15 centimeters. And I get around 4.4 maybe for a spring force for 15 centimeters. So again, it's increasing as we stretch. Now we're going to go to 20 centimeters, so 20 centimeters beyond equilibrium, and I get about, let me shake the friction out of the spring scale, somewhere around a little, maybe less than 6, well, looks like about 6. So at 20 centimeters, or 0.2 meters, I get about 6.0, okay? And I could continue that experiment. Maybe I'll do one more. So 25 centimeters, about 7.5. Okay, 25. Okay, not bad pattern here. This is 5 times as long, 5 times as much force. So we are seeing a sort of linear pattern. But to make a point, what I'm going to do is now show you with another spring, and we'll see that we get a different set of data. So it creates a different amount of force for the same displacements. So here is my relaxed length for this spring. I'm going to put a little mark right there, a little high, okay. And so now I will stretch this 5 centimeters, and here I get roughly about 2.5 newtons for 5 centimeter displacement. So for the same displacement, I get more newtons out of that spring. And let's go to 10 centimeters. About, looks like 4.5 for a 10 centimeter displacement, maybe 4.6. Let's try 15 centimeter displacement. And I get about a 7.1 newtons. 20 centimeter displacement. And I get about maybe 9.3. And so you still see that as this gets bigger, this grows by approximately a constant rate. Okay? If we were to plot those pieces of data, let me pause the video to give you a chance to copy that data table. Okay, and then I'll just create a real quick graph. F spring, X in meters. And the first set of data would plot something like this. Oops, let me do. The second set of data, for the same displacement, I had more force every single time, right? More force, so that would be like this. Still 0, 0 is 1 point, but for that same displacement, more force, more force, more force, and then we're already kind of off the charts pretty quickly. So if we do a best fit line for these two, I would get a straight line relationship. And then here, something like this. So this second graph represents a tighter spring. And this obviously a looser spring because it generates less force, but it's still a linear pattern. It's just the tighter spring goes up with a higher slope. Now in math, we can write the equation of a straight line as y equals mx plus b. So don't write this down because we're going to alter it. Okay. So the first thing, the line passes through the origin. So we can get rid of this, and our equation has that form. What do we have on the y-axis? Well, we have the spring force. And then the slope, we use the symbol K for when it comes to spring forces. So there is the equation for the spring force. Okay? So again, spring force depends on how much you stretch the spring. If you double the spring displacement, you double the force. If you triple the displacement, you triple the force. This is what's called the spring constant. It's measured in newtons per meter. We could tell that from the equation because if this is meters, then we need to have newtons per meter here, so the meters go away, leaving us with newtons on both sides of the equation. So newtons per meter, it's the slope of so that's just mathematically what it is. But what does it mean in terms of concepts? What it is it's a measure of how tight a spring is. And of course, x is spring displacement. In meters. So there's bullet 1, bullet 2. Okay. I'll pause the video to give you an opportunity to catch up. Okay, so this, if we were in the lab, we might get like a spring constant of 30 newtons per meter when we do experiments with this one. That's usually what pretty common. The other one, where did it go? Oh, here it is. This one was created more newtons for the stretch, so it has a higher spring constant. It might have like a 50 newtons compared to a 30 because this is looser than this one, okay? If we did an experiment with this one, instead of 30 or 50, this might be like 200 newtons per meter, okay? This one could be a spring constant in the thousands because of, I stretch it even 1 centimeter, 0.01, and I get maybe hundreds of newtons out of it. So that means that this has to be like in the thousands. So tougher the spring, the higher the spring constant. But the spring constant does not depend on the displacement. If this is a spring constant of 30, it's still a spring constant of 30. Spring constant of 30, right? That doesn't, when you stretch it, unless you break the spring, if I yank this and completely destroy the spring constant stays constant, right? Unless you damage the spring. Then it's broken, you have a different spring constant. All right, so let me do a couple examples. Okay, so there's the question. A spring generates 5 newtons when stretched 2 centimeters. How much force for 4 centimeters? Okay, so if you look here, we go back to the equation. We have 5 newtons for 2 centimeters, or 0.02 meters. You could convert, but it doesn't matter. The key idea here is that the displacement is doubling. So what happens if we double the displacement? Okay, what we have to do, since now we're going to be doubling the numbers on this side of the formula, because this is doubling, in order for this equality to hold, we've got to be doubling this side of the formula too. The only thing that can be doubled is the force, so it generates 10 newtons. So the answer here, you could just write, is F equals 10 newtons, double. You might be saying, hey, wait a minute, I thought I had to write an equation, plug in the numbers and all that. This is likely to be a multiple choice on the Regents, where you don't have to show the work. Just that you know if you're doubling the stretch, you're doubling the force. Okay? If you're tripling the stretch to 6 centimeters, we would triple the force to 15 newtons. Okay? Let's take a look at another example. Oh, I didn't pause. Hopefully you had that jotted down. Maybe when I put this in the Ed puzzle, I'll try and remember to put the pause in there. Okay, this is going to be about as hard as it gets with the spring force problems, because usually it's a pretty straightforward calculation. You're given 2 of these and then you have to solve for the third. But they could throw in a few extra curveballs, like in the following example. So let's suppose a 2 kilogram mass So a 2 kilogram mass stretches a 30 centimeter long spring to 50 centimeters, determine the spring constant. Basically, we're going to be using this formula. However, the 2 kilogram mass is kind of like the force or the load on the spring, but it's not in newtons, okay? And these are in centimeters, and furthermore, X is not the length of the spring, it's how much longer the spring gets. So we have to do two calculations before we even start using this formula. The first thing, displacement is going to be this length minus that length, but we also need to be in meters. So 50 centimeters is 0.5 meters, and 30 centimeters is 0.3 meters, which makes the spring displacement, if you punch it on a calculator, you'll get 0.2 meters. So there, that's X in the formula. The 2 kilograms, again, is not a force, that's a mass. That's what we learned about in the force of gravity video. So we need to determine, and of course, but the gravity is what stretches it, right? If I put this here and then I put a load on it, no, this is 1 kilogram, right? So the 1 kilogram in a sense stretched the spring, but it's the force of gravity, the earth pulling down, that's really stretching on this, that's stretching the spring. So the earth pulling down, of course, that's the force of gravity. And that's mg. And that's 2 kilograms times, that's m. G is 9.8. Remember, you don't have to remember the formula or those values. For example, the formula is right here, okay, right where my index finger is. G equals Fg over m, okay? Well, if you multiply the m to the other side, you get Fg equals mg, which is how I like to use the formula. But you could write it this way and still get full credit. And then the G being 9.8, I go to the front cover, and near the top, right here, I see little g, 9.81. Of course, I could use 9.8. By the way, the spring force formula we learned today is also on the reference table. It is right here where my finger is. Oh, let's see how to focus. Let's see, there we go. So there is the top of it. So it's near about 2/3 of the way or 3/4 of the way from the bottom. F spring equals Kx right there. Okay, so it is also on the back cover of the reference table. No need to memorize formulas in Regents physics. So back to the problem, you multiply this out, you get 19.6 newtons. And then, so finally now, I can use this formula for the spring force. F spring, Hooke's law, right? The spring is Kx. So I plug in my force of 19.6 newtons. K is what I'm looking for. And 0.20 meters, okay? So that is about K, if I divide both sides by 0.2, so or no, 98 newtons per meter, okay? So there's the spring constant for that particular spring. That's the spring force, our last predictable force that you can write an equation for. Remember the key points, F equals Kx. X is how much longer the spring gets. So here's X equals 0, not the length of this, but how much longer. So I go like this, and then I stretch it 10 centimeters, so X is 0.1. This depends on how tight the spring is. It's a constant based on the thickness of the metal coils. The bigger the number, the tougher the spring. Multiply those out times each other and you get the spring force, the force out of the spring. Okay, so that's it for today. I'll see you in the next physics video.